right, so the only purpose we are here is to help you learn this very interesting and also very useful class. So don't hesitate to ask any questions or give us any feedback, like whether I'm going too fast or too slow, whether you want us to cover something that's not in the posted schedule, right? Or yeah, just anything we can help. All right, so let's get started. The 2 lectures in this week, in the first week, focus on divide and conquer. It is a class of algorithm that usually involves recursion in the algorithm description. And Professor Devadas gone through several algorithms, including weighted interval scheduling and a bunch of others. And he left several open problems. So we will answer those open questions in this section, and we'll also show you a new algorithm and analyze a bunch of other algorithms. So just to remind everyone what weighted interval scheduling is, in this problem, we are given a bunch of requests. Each with a start time and a finish time. And our goal is to find a subset of them that are compatible, meaning they do not overlap, and that have a largest combined weight. Okay, everyone clear about that? So an easier case is when the problem is unweighted, meaning that, or you can think of every task has the same weight. In that case, we can just solve it using a greedy algorithm. But when the problem becomes weighted, we have to use dynamic programming or recursion. And Srini introduced a simple one, a basic version in a class. Can someone remind us how that algorithm works? Any volunteers? Mm-hmm.
For the next interval.
Can you speak louder?
We pick the earliest finish time for the next interval. So we find the next non-conflicting interval
Mm-hmm.
at the earliest finish time, and then we take that.
So what's your name?
Dr. Sai.
Uh-huh.
Then again, is that weighted? Am I correct?
Yeah, I think the version you described is for the unweighted case. In the unweighted case, we just schedule the earliest, the one with the earliest finish time, and then we remove all the incompatible ones and we keep going, right? That solves the unweighted version. If it's the weighted version, we need to use recursion. And remember, we break the problem into many subproblems, and each one can potentially be an optimal solution. Does anyone remember that? Can you give it a try?
Sure. So we break into subproblems, which is the best solution from a certain point.
Mm-hmm.
And then we calculate that subproblem starting at all the different finish times.
Mm-hmm.
We find the maximum of that.
Great. What is your name?
I mean,
What is your Amy? I mean, okay. I mean is that let's just try everyone as our potential first request. Okay. So if we choose request J as our first, we get its weight, right? And then we're going to solve a subproblem. So let me call the original problem weighted interval scheduling with all the incoming requests. Now we choose J request as our first. Now we are left with a subproblem that starts after request J finishes. So I'll write that as Rj, where I define Rj to be the set of requests where their start time is later than the finish time of the jth request. Okay, just to repeat, we choose a request as the potentially the first request, and then we look at all the requests that start after it and solve a subproblem of that case. Then we take a max of all the candidates we have, and that's going to give us the optimal solution. Any question about this algorithm? Okay, so this algorithm runs in n squared time. Now we are going to try to optimize that and come up with a better algorithm. So in order to improve anything, we first want to identify the inefficiency in this algorithm. Right? So which part in the algorithm do you think is inefficient or silly, unnecessary? Go ahead.
So it's inefficient to look through every previous subproblem when trying to find.
So you.
When trying to find the maximum for any particular subproblem.
Are you saying that we don't need to go through every of this case?
Yeah, we should. Well, we should be able to efficiently query for the right one.
Okay, I think you are definitely correct. So let me just go through what this algorithm does, and it will be more clear. So what this means is I'll choose the first request, request 1 as my first request. Then I'm going to consider only the request that starts after 1 finishes, right? That only leaves request 5. Potentially some others I didn't draw there. Okay? That's my first candidate in that max. My second candidate is I choose request 2 as my first request. Then I have to remove request 1 because it starts too early. And then I'm left with all the remaining requests. I'll solve that subproblem. That's candidate 2. Candidate 3, I choose request 3 as my first request. And then I have to remove 1 and 2 because they start too early. Oh, 4 as well. It also starts too early, right? Before 3 finishes. Everyone following that? So we are left with the remaining request. Okay? Is it more clear now? Go ahead.
So candidate, I mean, if you start with 3, that's actually a subproblem of 2. So you see that like you're doing a lot of extra work straight after.
Great point. So what's your name?
Andrew.
Andrew said we can potentially be solving many repeated subproblems, right? Because, yeah, we definitely don't want to do that. And that's actually the core idea, the one crisp idea of dynamic programming. Andrew, can you tell me what's the definition of dynamic programming? You don't remember? Anyone remember that? Go ahead.
You can just memorize subproblems, then look them up.
Exactly. So dynamic programming says we will break a problem into subproblems and subproblem into even more subproblems. But whenever we solve one, we should memorize or just remember its result and store it somewhere. And if you need it again, we'll just retrieve it, right, without resolving the problem. That's definitely a great point. So we can analyze the complexity of this algorithm later, because I want to touch on this more efficient algorithm first. And we'll see that even after Andrew's optimization, its runtime is n squared. So without that observation, if we are solving repeated subproblems, it will be a lot worse than that. Anything to yeah, go ahead.
You can also trim ones that like get to the same place, so you don't need to explore 2 paths.
Sorry, say that again.
You don't need to explore 2 paths that get to like both explore and free. Once they're both looking at free, then you only need to do the one that's more efficient to that point.
Okay, cool. Go ahead. Oh, the same thing?
Well, I have another one as well. So I think to get better than n squared, I think we need to make the observation that it's
Okay, great. Yeah, I think we are on the same page. So when I describe the steps of this algorithm, remember the third candidate, I choose this as my first, right? It makes 0 sense. Because if I do that, I might as well put in 2 as well. Doesn't hurt, right? Everyone get that? So yeah, the idea is that we shouldn't try every possible request as my first. Some requests are just better, more suited to be the first request. And how we are going to do that? So apparently 1 can potentially be the first request, 2 can also be, but it doesn't make any sense for any request come after that, because there's an earlier request, right? So the efficient algorithm, let's first sort them by their start time. We are going to consider the request that comes early first. So I have my entire problem here. Now I'm going to ask a question. Should I include request 1 in my solution or not? That's only 2 cases. So if I do not select 1 in my solution, what subproblem am I left with? Any idea? If I decide I will not include 1 in my solution. Yeah, exactly. Because there's no conflicts anywhere. I'll solve a subproblem from 2 to n. If I do decide to put my request 1 in the solution, I get its weight. So what's the subproblem I'm left with? Yeah, in this example, it's 5, correct? But more generally,
The way you define RJ, so like every request that starts after 1 finishes.
exactly, every request that starts after 1 finishes. Okay. Now suddenly we are not breaking the original problem into n subproblems. We only have 2 subproblems. So let me draw a recursion tree, which is a powerful tool in analyzing this sort of things. So we start with our original problem from 1 to n. And we have 2 subproblems, 2 to n and R1 to n. This one, we'll also break them into subproblems. So what is this one? Okay, I have my subproblem 2 to n, and I need to further reply the same trick.
There's only 1 child.
Mm-hmm.
It would just be for WIS, the max of WIS 3.
Oh, sorry. These are the 2 cases, right? Either I do not schedule my first, or I schedule it, and it's my first request, right? Now here, I'm left with this problem. Either I do not schedule it, or I schedule it as my first request. So what is this one?
Oh, it'd be 3 to 3n.
3 to n, okay? Because now I'm asking the same question for 2. And here, I'll have R2 to n, so on and so forth. Now, let me point out the big difference for this version and for the basic version. So I'm starting with the request that starts first. If I do not do that, say if here I'm asking the question for 5, do I schedule 5 as my first or not? Then what happens? then these two branches do not cover all the cases, right? Because I can potentially schedule it, but not as my first in the optimal solution. If I'm asking a question for a random request. However, if I start with the first request, first meaning it starts earliest, it will either be not scheduled or it will be scheduled and as the first, because it cannot be the second request in my solution. Any questions about this algorithm? Okay. Now this is algorithm. Let's analyze its complexity. So what's the overall complexity when we go all the way down, solve the entire original problem? Any guesses? What do you think? What do you think? Go ahead.
It should be n log n, because we're going to need to sort the intervals.
Mm-hmm.
And we're going to need to, for every interval, find the next interval that starts after it finishes.
Okay.
And we can do that for everything in log n.
Cool. So because the first step is sorting, which is n log n. Now, after I sort everything, the question I need to answer is how many unique subproblems are there, right, in this entire recursion tree. So I'm not going to solve the same problem twice. How many unique problems exist here? N of them, right? Just this left branch, okay? All the others will be one of these. Right, so I can start from bottom, the bottom of the tree, and work my way up. And when I want to go take this step, I'll look up the result of this in one of the subproblems I've already solved. Okay? So actually, the recursion itself is only O of n. Questions?
What is the sorting referring to?
Okay, so we need to start with the request that starts first, right? We need to decide whether we schedule it or not. And then we need to do the same thing for this request 2. It's the start earliest request in this subset. We always need to do that for all the subproblems. So the overall complexity is n log n. But if we only focus on this recursion step, our improvement is actually larger than that, because it went from n squared to O of n. So why is the original algorithm n squared? I think it also has only n unique subproblems, right? So do you agree that the original algorithm is n squared? Or do you think it's also O of n? Just focus on the recursion step.
In the
Go ahead.
original algorithm, you solve some problems up to n times. So that's why it's still O of n squared, because you solve the same thing n times.
But assuming I do not do that, assuming whenever I solve it once, I store the result somewhere, and I directly get it. Okay? Assuming I do that, what's the complexity? Go ahead. Uh-huh. You think it's O of n? So anyone think it's n squared? Because I think Srini said it's n squared. Okay, go ahead.
So yeah, like I think the original algorithm isn't still n squared because we're still doing O of n work for every subproblem group.
Exactly right. Yeah. So here, whenever we go up one step, I'm doing constant number of work. Right? I'm just comparing two numbers and taking the max. However, in the original algorithm, which is here, whenever I want to go one step up, there are n branches of the tree. So my total amount of work is like 1 plus 2 plus 3 plus n, right? every step becomes harder when I go up. And this is n squared. Any questions about that? Okay, this is so much for our weighted interval scheduling. Now I'm going to transition to the next topic. So any question on this side in general for the scheduling problem? Do you have a question? No? Okay. Yep. Now let's turn to a second topic of this section, which is Strassen algorithm. Strassen algorithm is an efficient algorithm for matrix multiplication. And matrix multiplication is a really useful primitive, or it has applications in almost every area. Like I can think of circuit simulation, climate simulation, and physics, basically everything. Now, I actually had some experience with matrix multiplication because my undergrad research was improving matrix algorithms. And actually many matrix algorithms, including like inversion, solving equations, they all use multiplication as a primitive. So it actually comes down to improving matrix multiplication. And I tried very hard to just optimize this basic matrix multiplication. You take a row, you take a column, and then you get your answer for this spot. And everyone's familiar with that, right? I tried very hard, but it's still 100x slower than the best algorithm out there. So I finally looked it up, and I was completely mind blown when I know that matrix algorithm complexity is not n cubic. It's actually smaller than that. Is this a surprise to you? Anyone expect that before? And the technique the more efficient algorithm uses is exactly Strassen algorithm. Now that we're talking about divide and conquer, you can guess it must be a divide and conquer algorithm. And so does anyone have an idea how to divide the original problem? You want to give it a try? So are you familiar with tiled matrix multiplication or blocked matrix multiplication? Okay, can you tell us what that is?
Yeah, you can break it into like quadrants essentially, and then their identities or half of
Okay,
can multiply.
cool. So say this is our A and B, and we want C. We can break each matrix into 4 parts. I'll call this A11, A12, A21, A22, B11, B12, B21, B22. Same thing for C. Now, I would like someone to tell me what is C11 in this case. Go ahead. A12, B21, yeah. And C12 is, just speak up, don't be shy. Okay, this is also my first section ever in my life, teaching a recitation. I'm more nervous than you guys. What is C12? A11, B12, A12, B22, right? So the rule is the same as before, matrix multiplication. Compute this, we take this row, this column, and it gives us this. Right, thank you. A12, B21, right? A11. Okay. And same thing, C21, we're going to take this row and this column, A21, B11, plus A22, B21, C22 is A21, B12, plus A22, B22. Okay? Everyone understands this? Okay, great. So now we've broken up the original problem into several subproblems. We only need to do matrix multiplication here 8 times. And each of this matrix is half in size. Right? If the original algorithm is in cubic, now each subproblem is half n cubic. Then we have 8 of them. So the complexity is still n cubic. No improvement at all. So actually, to be more precise, we should, because we can further break up these matrices into smaller blocks. So to be precise, its complexity should be given by a recursion, right? 8 subproblems, each one half the size, plus, can anyone tell me, what's the merging complexity once I get all this? All the go ahead.
Just constant because you're adding, or?
Yeah, because I'm adding, but is it constant? I'm adding these 2 matrices.
For the base case or for each level?
Pardon?
For each level or for base case?
Yeah, for base cases, of course, constant. Okay. So maybe I'm not clear about this. What's the subproblem in this case? It's this multiplication operation. Okay. And so these are the 8 subproblems I will solve. After solving them, I need to add them together. And adding 2 matrices, and each is size half of n, the complexity is, yeah, it's n squared. Basically n squared. Right? So to get a precise complexity, we should solve this recursion, but it will end up being the same thing as this intuition in cubic. Okay, so now this is the magic. So Strassen in 1969 came up with this algorithm. And each of these is a half n by half n matrix. Okay. Okay. Cool. So Strassen came up with this algorithm. He somehow defined M1 through M7 7 matrices in this way. I can't provide any intuition because I didn't come up with this. And somehow, with those 7 matrices, he can compute all the 4 submatrices in C. And it's not very interesting to check it because the algorithm is definitely correct. But let's just do one of them. Okay, how about this one? So C21 is M2 plus M4. It's M2 plus M4. So M2 have A12, B11, A22, B11. So there's M4, there's A22 minus B11. So that cancels out. Right? So we are left with A21, B11 plus A22, B21. That's the correct answer. So this is I guess it's a very clever algorithm. You have to work in that area for 10 years to come up with this. So that's not our concern. Our goal is to analyze this algorithm. What's the complexity of it? So does anyone understand this recursion? Can someone tell me what's the recursion for this part, for this Strassen algorithm? So we have the original problem. And we have some, go ahead.
So since each of the like n1 through 7 only require one multiplication,
Mm-hmm.
we only need to solve 7 subproblems. So 7t n over 2 plus O n squared n4.
Yeah, that's absolutely correct. Everyone gets this? So what Strassen did is he came up with the 7 matrices. Each one requires only one multiplication. So we have 7 subproblems instead of 8. And that's going to give us a benefit, an improvement. Now, so the question now becomes, how do I solve this recursion? Right? Given this recursion, how do I know its complexity? And same question there. Anyone want to give it a try? So that's going to be covered in the third topic. What can I erase? Which is master theorem. So master theorem does exactly that. All it does is, given the recursion A and T of n over B plus some work for merging, where A and B are constants, it directly tells you what Tn is in some cases. So I'll first write the formula. Master theorem actually has 3 cases. The first case is Fn is order n raised to c, where c is less than log b of a. Then master theorem says its complexity is theta log b of a. Second case, Fn is theta, then c log k, where c is log b equal to b of a, then its complexity is n raised to c log k plus 1. And you don't necessarily have to copy them because you can just find it anywhere. And the third case, you can imagine, is the only remaining case, which is Fn is large, is omega, n raised to c, where c is greater than log b of a. Then master theorem says its complexity of the complexity of Tn is theta Fn. So intuitively, if Fn is not too much work, then it's basically this recursion, what recursion gives you. If Fn dominates, Fn is the biggest component, then Tn is roughly on the order of Fn, and there's a case in the middle. Now let's see why that is the case. I'll only cover one case here. So again, we are going to draw a recursion tree because that is very useful in all the recursion problems. So we start with a problem of size n, and we break them into problem size n over b. So on and so forth. What's the size of this subproblem? So that recursion represents a class of recursive algorithm. Every time it breaks the problem, it reduces the problem size by a factor of b. So what do I have here? Go ahead. n over b squared, so on and so forth. So what is A in this graph? Go ahead. 3? Think so? 3. Right? A is just a branching factor of this tree. Right? I keep going. Finally, I will reach my base case. So my next question is, after how many levels of recursion will I reach a base case of size 1? Go ahead. Log B of log B of. Okay, so because here is n over b squared, next one n over b cubic, so on and so forth. So for the, say this last level is tth level, then the problem size is n over b raised to t. And we want that to be a constant. So what is t? Log b of n. Now this is the recursion tree, and we have that fn amount of merging work to do. So here we have to do fn work, right, to merge these A results to the solution of our problem n. And we have f. What's the merging work for this level, for this part of the tree? This is my problem size. N over b. Right, and we have A of them. Okay? So on and so forth. So then we know what is Tn. Let's just enumerate all the work we have to do. So on the first level, we have to do Fn. Okay, on the second level, A, F, n of b, n over b. And what's the next level? We have how many subproblems? Speak louder. A square subproblems, and each of them is n over b squared. And finally, I reach my last level. They are all base cases. So I have A raised to t of them, right? Because I define t to be my depth of the tree. And each of them is t of 1. Okay, so that's Tn. I'm not entirely happy with this formula because I have this beautiful pattern here, right? Except for that last guy. It's A, add 1A and divide 1B, blah, blah, blah. So I'm going to change this T into F. Can I do that? Because asymptotically it's the same, right? T1 is a constant, F1 is also a constant. Then I get my beautiful form where it's a sum from I equals 0 to T. What's in the sum? Go ahead. A raised to I, F n over bi. Everyone gets that? Now you can roughly see why we have 3 cases. So let me deal with the first case. The first case says Fn is order n raised to c. Right? What does that mean? It means this guy here is sigma a raised to n, then this is what's in my f raised to c. Okay? There should be an order here, but everything has an order before it, right? So I just omit that. So it actually should be this. Okay? So this because n raised to c is actually independent of this sum. I can pull it out. And what am I left with? Is that correct? Now this is a sum of geometric sequence. Right? We know how to solve that, right? But we need to check whether this ratio is greater or larger than 1, or if it's equal to 1. And what is this ratio? The case tells us. Right? So c is less than log b of a. That means if b raised to c is less than b raised to this guy, which is a, right? So we know our denominator is greater than our, is smaller than our numerator. So this is the increasing sequence, right? So what we have is n raised to c, then that thing raised to t minus 1 divided by this thing minus 1, but they are all constants, right? Everyone familiar with this formula of geometric sequence? Okay, so that's what we have. Next, we have t equals log b of n. That means b raised to t is n, correct? So then b raised to t is n, then we have raised to c, cancel them, they cancel out. What do we have? I want to make sure everyone is following. A raised to t. No questions?
Can you do that step again?
Okay, let me do that again. Okay, it's actually a raised to t, and then n over bt raised to c, right?
How did you get from the line above that?
This one to here?
Yeah.
Oh, it's the sum of geometric sequence. So if I have 1 plus q square plus all the way to qt, it's qt plus 1, I guess, or t, I don't remember very well, minus 1, then q minus 1. Okay, I guess this should be t plus 1, right? Okay, so this is what we were doing. So this is our q minus 1, and divided by q minus 1, they are all constants, so I don't care about them. So a raised to t plus this thing raised to c, but we said that b raised to t is equal to n, so we're just left with a raised to t. And what is t? T is log b of n. I can write it as log a of n over log a of b. Everyone familiar with that? That means log a of n log b of a. Okay, this one I flip them, so it. So this, what is that? That is n. Okay, we're done. Are we? Not exactly, because I have an order here, right? So everything is order. If you only care about order, big O, then it's fine. But that theorem says theta. So you have to prove it the other way, that it's no less than that. Okay? But I'm not going to do that. It's not very hard. Next, I'm going to apply this theorem to the two problems we left here. So let's apply master theorem to this recurrence. I think you are still looking at that side. So what is the A, B, C for this? A is 8, B is 2, right? And C is 2. Log b of a is 3. So that's the which case of the master theorem? Okay, so the theorem says it should be n raised to log b of a, which is 3. Okay. Now, what we have here, can I invite someone to do that for me? Want to give it a try? Yeah, go ahead.
Okay, so we have a equals 7, b equals 2, and c equals 2, like before. And now we want to see whether c equals 2 is less than log b of a, which is log 2 of 7. And pretty sure that's still the case. So we should just get n to the log 2 of 7.
Yeah, exactly. So yeah, log 2. Yeah, thank you. Let's give him a round of applause. So log 2 of 7 is definitely greater than 2. Why? Because log 2 of 4 is 2, right? So this happens to be n raised to 2.80 and many other digits, but it's less than n cubic. And just for knowledge purpose, this is no longer the best. It was the best when it was proposed, and well, researchers in that area has got it down to n raised to 2.35. I think 2.37 first, then 2.35. I'm not following the literature very closely, so maybe it's 2.34 now. Okay, so I should have one more thing to cover, but I think we are running out of time. Sorry about that. I can post. So the last thing we should do is remember we have this median finding algorithm where we have a recurrence, which is, I think, n over 5 with some seeding, and then plus this, right, and plus some theta n. And we want to solve this recursion, but we cannot apply master theorem, right? Apparently, it's not the right form. So we have so when master theorem doesn't apply, we have to study it case by case. Let me see if I have time to do that. Okay, I think I probably do. So to solve that case, first, can someone tell me what's the definition of theta? We have to go back to the definition to solve that. What does theta even mean? So if I say Fn is theta n, what do I really mean? Go ahead.
It's tightly bounded, so both are, you can move the big O either side.
Great. So it means I can find some k1 and k2 such that this holds when n gets sufficiently large. Okay? So now we're going to do an induction. Assuming for all the small n less than capital N, my Tn is bounded by this k2 and k1 thing. Okay, then my next step is T of this capital N would be bounded. I'll do the right side first. Will be bounded by k2 and 5 seeding plus k2, like things in that in the second term, and plus another theta n. So we know that means it's bounded by some other number. I'll say a2 then. Okay, that's the definition of theta n. Then can I find, I want this to be, sorry, all of them should be capital N, capital N, capital N. I want this to be smaller than K2, capital N, right? Because this, so let me redo this first step. This is roughly 5 of K2 plus 7 over 10 K2 and plus A2 of N plus a bunch of constants that I don't care. I want it to be smaller than K2 of N. Can I reach that? Of course I can, right? If I select K2 to be greater than all we have here, right, what is this? This is 9 over 10N, 9 over 10 K2 plus A2, right? So if I select K2 to be greater than 10 times A2, is everyone following that? When n is sufficiently large, Tn should be bounded by K2n, right? That's my, that's the induction. I'm assuming when n is smaller than capital N, I have solved them, so I can use these two, and I show the next step. So there's the other side, which is very similar. I'm not going to go through that. All right, so that's all for today. And just to quickly recap, we went through the weighted interval scheduling, and the Strassen algorithm, master theorem, and applying master theorem, and that a case study of a new recursion. Okay, thanks everyone for coming.
The following content is provided under to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
So all right, so this is a 2-3 tree. So as you can see, every node has, so the 2-3 is either 2 children or 3 children. Every node can have either 1 key or 2 keys. And the correlation is that every, so if there are n keys in a node, it has n plus 1 children. So the way that works is, well, it is similar to binary search trees, right? So if you have value here, the 2 children surrounding it, so this side is less, this side is more. So it's essentially in sorted order, going in an in-order reversal. So left child, root, right child. So in order, it's sorted. So generally, a B tree will have some nodes. So let's say n and n plus 1 children. And if you take anything in the middle, look at the 2 children. All the keys in this subtree are smaller than the key here, and all the keys in this subtree are larger than the key here. So that's the general node. Okay, so before we go into more details of the properties and everything, so the question is, why use B trees? So let's, like, if we do a quick depth analysis, we can see that the depth is still log n, right? Is that clear to everyone? Sort of why the depth is log n, because you have branching just like in binary search trees. In fact, you have more branching, but in any case, the depth is still log n. But why use B trees over binary search trees? Anyone have a reason why you would prefer to use B trees and not? So like all the operations are still log n. Any guesses? None? Okay. Well, okay, the reason is, well, memory hierarchy. So normally in algorithms, we just assume that the computer has access to like memory, and you can just like pick up things from disk and constant time and do your operations with it, and you don't worry about caches and everything. But that's not how computers work, right? So in a computer, you have, so those of you who have taken like some computer architecture class, 604 or something, you will know, so that hierarchy. So there's a CPU. So let's draw it somewhere. So you have your CPU, and near your CPU you have some registers. You have your caches, L1, L2, L3, whatever. You have your RAM. You have disk after that. So disk is the slowest. Then you have your, I don't know, your cloud, whatever. So like each level, your memory size grows and your access time grows as well. So in the basic memory hierarchy model, we have just 2 levels of hierarchy, let's say. So you have cache connected by a high bandwidth channel to the CPU, and you have a low bandwidth channel to disk. So the difference is, so essentially you can consider that cache to have like infinite speed. Cache just like whatever you can take, you don't have any cost for bringing in stuff from cache. So, but it's finite size. So the way cache works is it has a bunch of words, which is a finite number of words. So each word has size b, and let's say you have m words. However, hard disk is just, let's say, infinite memory, but it has some cost associated to accessing things. Okay. Also, when you access things from hard disk, you copy them into cache, and you copy a block of size b. You take it up from the hard disk, and you take a block and you put it into cache, and you have to get rid of something because it's finite. So what you want to do is you want to utilize that b block efficiently. You don't just want to like bring a b block every time you want to access a new node. In a binary search tree, like normal operations are what? You start at the root, go to a node. So, but that's not very easily correlated with this, right? So if you want to utilize the entire block, you would want something like a block which sort of goes down the tree. But that's not how binary trees are stored. Binary trees are stored this way. So that's the nice thing about B trees. So since you can make, so this is just a 2-3 tree. This is not a general B tree. A general B tree will have a bunch of nodes, and we'll come to that number. But generally, you want to make that number of nodes something like the cache. What is the cache? The word size in the cache. So once you do that, you can get an entire node from disk, like work on that, and then like get another entire node. So like your height is reduced, and you can do your operations much quicker because you are not accessing disk every time you're going down a level. I mean, you are accessing disk every time you go down a level, but you're utilizing the whole block when you're accessing disk. Good? Sort of make sense? Okay. So let's write down the specifications for B trees now. All right. So number of children. So, okay, first of all, a B tree has something called a branching factor. So in the 2-3 tree, the branching factor is 2. So what that means is simply it just bounds the number of children. So the number of children has to be greater than or equal to 2, other than the root node. The root node can have less than b children. That's fine. Also, it's upper bounded by 2b plus 2b. Notice that this is a strict upper bound. So you can have at most 2b minus 1 keys in the children from a node. Also remember that the number of keys is there's just one less than the number of children. Therefore, these inequalities. Oh, that's not right. There we go. These inequalities just get reduced by 1. So you have 1 minus 1, and you have 2b minus 1. So number of keys can be between b minus 1 and 2b minus 2. The rationale for that will become clear. Oh, yeah, no, b is the branching. So b is the branching factor. So that is the number of children. Like it's not a number of children, but it's a bound on the number of children. So like in the 2-3 tree. So b is equal to 2, and this is a 2-3 tree. So the 2 refers to you can have either 2 children or you can have 3 children. So here the upper bound in children is 2b minus 1, right? 2b minus 1 is equal to 3. So you can have either 2 or 3 children. And correspondingly, you can have either 1 or 2 keys in the node. Make sense? Cool. Okay. So coming back to this. So the root does not have the lower bound. The root can have 1 child in any tree. So you have a b equal to 5 tree, the root can still have 1 child. Not 1 child. 1 key element, 2 children. All right. That's good. Also, it's completely balanced. So all the leaves are the same depth. So like you can see it here, right? So you can't have like a dangling node here. This is not allowed. You have to have a leaf. You have to have something going down, and everything ends at the same level. All right, so that's the thing. So also the leaves obviously don't have children, so this condition is violated by the leaf. Okay, all right. So that's the basic structure of a B tree. Now, so the first operation we'll consider on B trees is searching. So that should be relatively straightforward, right? So remember how searching is done in the binary search tree. You bring in a value x, compare it to the key. Let's say x is less than k. You go down this path. Let's say x is greater than k. You go down this path. So similarly in a B tree. So let's say you bring in a value. Let's say you are looking for 20. So you bring in 20. Compare it to this. 20 is less than 30. So go down here. Now you have two values. So where does 20 fit in here? Not here. Not here. It fits here. Okay, go down this tree. You find 20. That's it. So in general, you bring in a key k. You look at this node, and you go through all the values. So something I forgot to mention. So which should be clear. All the keys in a node, they're sorted, one after the other. So your values go like this. So they're increasing in this way. Make sense? Okay. So you bring in a key. Look at all the keys in the node you're looking at. Pick the place where k fits in. Unless it's already in the node, then you're done. You found it. Otherwise, let's say the k fits in between these two guys. So you go down this child and continue. So searching is log n, similar to BSTs. Okay. Okay. So searching is not very interesting. So let's see. So next is insertion. So insertion is a little more interesting than searching. So what you do in insertion is you.
Sorry to interrupt a little bit. So we didn't book this room, and people, have booked this room for recitation.
Oh.
In 2 minutes.
Okay.
They start only 11:30.
Well, I guess we start to run again. Okay. Should we move back to the original room?
Move back, yeah.
Okay. Let's do that.
Sorry for the hassle, guys.
So before we resume, does anyone have any questions about the structure of B trees? We rushed through that quite a lot, quite fast. So about how B trees are structured. Everyone good with that? Okay. Also, any questions about searching in a B tree or a BST or anything? Go ahead.
Just a random question. So the 38 there,
Mhm.
it can only have 2 children.
Yep. So one value, 2 children. So whatever is, so you have some node in the B tree, and whatever is below it is split into parts by the elements. So if you have n elements, it splits it up into n plus 1 segments. So, okay. All right.
You said that the root didn't have to follow the rule?
No.
Why is that?
Well, you'll see when we do insertion and deletion why that's necessary. But essentially, you can consider that it's an invariant, and all we have to do is preserve that invariant. So yeah, the root has to still have less than 2. It still has to have the upper bound, but it doesn't need to have a lower bound. Okay.
How do you choose B?
Yeah.
How do you choose B?
The whole interlude about the cache size. So something with that. So you probably want 2B to be about your cache size, so you can get the whole block in one go. I've never implemented a B tree, so I don't know how it's actually done in practice, but that is the reason it's done. So I'm assuming it's something to do with the cache length. Hmm?
It's the 14. Is it a child of both 10 and 10?
Well, it's not a child of either. It's a child of this node. So this node has 2 elements, so it's being dividing the interval up into 3 parts. So it's a child. It's in between 10 and 17 is the point here.
So then this node has 5 children?
Sorry? No, it has 3 children. So don't think of every key as a node. Think of the whole unit as a node. Okay. So it's not, so in a binary search tree you have 1 element, but here every node has multiple elements. That's the point of it. Okay. Anyone else? Okay. Let's start with searching. So you have the formulas up there, so that's good. Okay. So, insertion. Let's start with insertion. We already did searching. Okay. So insertion is you bring in a new key k and you want to insert it into the tree. So what's the problem that could happen? You can find the location where you want to insert it, just like searching, right? You just go down the tree and find where it should be placed. But once you do place it, you'll have a problem. What is the problem? The problem is that one of your nodes will become overfull. And that's not what you, or whatever, it'll overflow. And that's not what you want. So you want some way so you can manage that. So how do you manage that? So I have this lovely prop here, which I'll hope to demonstrate. Yeah, that's the one. Okay. So here we have b equal to 4. So let's first figure out the number of keys. So what is the minimum number of keys, anyone? For b equal to 4? 3, precisely. So what is the maximum number of keys? 4 into 2 minus 2, yeah, correct. 3, 4, 5, 6. It's not 7. There's a strictly less than sign somewhere. Yes. And you'll see why it's not 7 in a bit. Oh, well. Hypocritical of me. Okay. All right. So as you can see, 1, 2, 3, 4, 5, 6, 7. So some insertion happened. Is the writing clear? Can everyone read the numbers? Good. Okay. 49 looks a little skewed. Anyway, essentially these are all sorted. This is the parent node. Doesn't matter what's over here. All that matters is 856 and whatever is in between. Okay. Now, so what we do when we have an overflow node is something what's called a split operation. So split. And there's something which is called a merge, which we'll come to later when we're doing deletion. But now, so split is very intuitively, it splits the node into 2 parts. So what it does is when you have an overflow node, the number of elements here is what? 2b minus 1, which is just 1 over the max. So what you do is you take the middle element and remove it. And now you've split the node into 2 parts. Observe that there are 3 here and 3 here, which is perfect. And now what you do with the middle node, so now you have actually disrupted the structure of the tree. Because there was 1 pointer going in, there was 1 child, and now you have 2 children. So somehow you need to adjust the parent node, because the parent node had only 1 child. Well, at least there are other children off to the side. But here it had only 1 child, and now it's split apart. So you do something very simple. You just insert this guy in here. And then you say, oh, this point's here, and this point's here. Make sense? I'm going to get rid of these 2. Okay? So, and like you can convince yourself that this preserves all the nice properties. So your children have nicely fallen back into their interval. Your sequence is completely correct because this was the middle element of this, so this divides this interval properly. This is also between 8 and 56 because this was in this node. So all the properties, but there's one property that is a problem. So you've just increased the size of the parent node by 1. So now it's possible that the parent node has overflowed. So what do? You split it again. And you split it again. And if at any point you're fine, you look at the parent node and go, oh, okay, that's fine. That's in the range. But every time it overflows, you can keep going. And how many times can you do this? You can do this all the way up to the root. And when you reach the root, either it's fine or the root is too big. It's reached to 2b minus 1. And then you split the root and you get 1 singleton node up there. So that, in answer to your question, that is why you need that property in some sense. Not a very convincing argument, but sort of handy. But anyway, so let's actually do an insertion in this tree we have here. So we are going to insert 16. Okay, so 16 comes in here. It's less than 30, goes to the left. It's between 10 and 17, goes in the middle. 16 and it's greater than 14. So we add 16 here. Oh wait, no, never mind. Oops, sorry. Just a second. Yeah. Okay, no, that's good. Yeah. All right, that seems good. All the property is fine. This is still has 2 elements, which is the maximum, but it's good. It doesn't overflow. Okay, let's insert something else. Let's insert 2. So 2 goes to 30, goes down, and we have a problem because 2 has overflowed this node. So we split, and the way we split is we take the middle element. So we split the node here. Good. And 3 goes up to the parent. So 3 goes here. And all good, except for the parent is overflowed. So what do we do with the parent? Well, we split the parent again. And this time I split it down the middle. The 10 goes up. So, okay, let's get rid of this. Yeah. So now that we split the parent, the 10 goes up here. And you're good. It's a bit cluttered, so let me reposition the 17. Okay. Did those 2 operations make sense? Questions? Yeah, so just pick the, first of all, okay. If the way we are doing it, when your node is overflowing, so you're inserting only one thing at a time, right? Yeah. So if your node is overflowing, it'll be 2t minus 1, which is an odd number always. There might be a case where you get an even number if you do something weird. Maybe you have it like, there are like different ways to do B trees, but if it does, you can probably pick the one, like either of them, and then the split will similar. I'm not sure about that. I'll look into it. But in general, if you're doing it this way, it's always odd. So you don't have to worry about that. Good. Anything else?
If we did reach all the way to the root and then went one more up.
Yeah. So what you would do is
that root would have
2 children, one element and 2 children, which is fine because we didn't put that restriction on the root. Okay, that's good. How are we doing on time? Okay, you have some time. All right, let's jump into deletion unless anyone else has questions. So what? Oh yeah, that's a good. Thank you. So you are going down to the leaves at most, at most of the leaves once, and you're going back up once. So it's like log n plus log n, and you're good. Okay. Good. Okay. Let's do deletion. Okay. So deletion is more complicated. So the reason is, it'll be clear. So what the problem in deletion will be remove a node, and a node is now underfull. So it has less than b minus 1 keys in it suddenly. So let's turn this around. There we go. Is that good? Okay, good. So again, b equal to 4. This node is the problem. Only 2 things in it. So what do we do? Okay. So before we go into that, let's make this assumption that, okay, so there are 2 steps to deletion. The first step is making the deletion at a leaf. How do you do that? So the way you make the deletion at a leaf is, let's say you have a key, you come down your binary, B tree, and you're at a node. Now this node, you guys, oh, this key needs to be deleted. But it's not the leaf. So what do? So essentially what you do is you look at these 2 subtrees, right? So it might have only one subtree. If it's at the end, it'll have only one. Actually, no, that's not true. Never mind. Ignore that. If it's not a leaf, it has 2 subtrees. So either take the rightmost element in this subtree, which is a leaf, because you can always keep going down right till you get your leaf, or the leftmost element in this subtree. So that is just the next element after this guy. So you delete this, and you bring this up to here. We'll do an example of this, and it'll be clearer. But you take either the rightmost element in the left subtree or the leftmost element to the right subtree and bring it up here. So you sort of like move the deletion to the leaf, and now it's easier to deal with. So we will come to that. Also, just note that this is not what is done in the recitation. This algorithm for deletion, I think, is not done in the recitation notes. This is a different thing, which I'll send out a link for later. But I believe it works because I got it from the. I'll tell you a reference. Okay. So once you move to the leaf, so now let's look at this. So this is a node that is under full, and you want to fix it. So how do you fix it? So what you do is you look at its siblings. So in this case, it has one sibling. It can have up to two siblings. It can have the left or the right. Okay. So what you do is you look at a sibling, and this sibling is actually 1 over the minimum. And if it's 1 over the minimum, then it's really easy. All you have to do is take the leftmost thing here, or if the sibling is on this side, take the rightmost thing here. And look at its parent. So you bring the parent down, and you move the sibling up, and there we go. So you basically so you are rotating the thing into place. So you move the parent down into the under full node, and you replace the parent by the leftmost thing here. Everyone see why that preserves everything? Okay, and also okay, yeah, and the child is also shifted. Make sure you see that. So like the child which was in this subtree is now in this subtree. All right, but then you can have the situation where you don't have a nice sibling to take care of your problems. So in like this scenario, this sibling is like barely full. It has 3 things in it, and it can't donate anything to you. So what do you do in that case? So then you do something which is a parallel of the split operation. You do a merge. So what do you have? So here you have b minus 2. And here you have, well, b minus 1. And you get 2b minus 3. Well, you get another element. You also take the parent. So how you do the merge? I'm just going to show you the merge first. So the way you do it is you move the parent down, and you merge these two. Oop. Seems okay? So you move the parent node down, merge these two. And, well, now this comes together. And this points into the new node. Sort of clear what's going on? Questions? Well, so you have yeah, exactly. So you have decreased the size of the parent, so it might not be under full. So you propagate. Anything else? Sure.
Wait, so are these all different techniques for deleting?
So there are 2 cases, right? So either you have a sibling which has extra nodes to donate to you, or you don't. If you don't, then you have to do this.
What about that case? What about that case? Or is that just like?
No, that is moving it down to the leaf.
Oh, okay.
Once you move the deletion down to the leaf, so here you have something. Propagated the emptiness upwards. Now you take this empty node, and you look for its siblings. Again, its sibling is, well, it's barely full. So what do you do again? You bring the 30 down, and you merge this. So let's do that. So $30 comes down, and there we go. All the looks fine? Does that tree look good? Questions about the operation? Yeah, I'm sure it was not clear, but anything? Make sense? Okay, let's do a deletion where we can actually do a rotation. So let's go ahead and delete 20. So you do your searching, go down the tree, you find the 20, and delete it. It's gone now. Okay. So you're left with just, actually, never mind. We'll do another one. So this doesn't do anything. You lost the 20, and you're left with the 24. That's fine. So now we delete the 24. So now that you got rid of the 24, you have a blank box here now. But its sibling is not barely full. It has something to donate. So what will it do? So anyone, which elements are going to rotate? 16, 17, right? Okay, cool. So 16 goes up, 17 goes down. And you're done. You're consistent again. Okay. So that was deletion. So those are the 2 cases for deletion. Does that make sense? Everyone? Any Any questions? Okay. So that's all the topics we were supposed to cover today. Any questions about any of the operations, any of the other topics, lecture, anything?
The following content is provided under a Creative Commons license.